In this segment, we'll wrap up our discussion of the top half of herd animal, and we'll look at two new design patterns illustrated by that code. Now, at the end of the prior segment, we discussed the abstract method isGoodLeader, which was in herd animal, and that was an example of template method design using an abstract method. And we said that subclasses of herd animal would have to override isGoodLeader to provide code. Now let's look at two examples of that. First, there is cow. You have enough information to understand most of its code already. Look that code over and then answer a couple of questions. And we'll put it up here for discussion. So the first question, is it okay for a subclass to override a method in its grandparent superclass, or even further up the inheritance chain, even if its immediate superclass does not do so? And returning from a pause there, well, yeah, given that cow's getLabel is overriding animal's getLabel, cow here, animal up there, without herd animal overriding getLabel, there was no getLabel in herd animal, then apparently it is allowed. In general, you can override any method up the chain above you, as long as it's not final or private. And then question 2. Is it true that leader, LDR here, in isGoodLeader, despite being a herd animal, will actually always be referring to a cow? Is that true? Why or why not? And if not, what else could it be referring to? Turning from a pause there, the call of isGoodLeader is made from herd animals step method, right? Where is that? Right in there. On members of list all from up here. And that list may well be a mixture of horse and cow objects. It won't be a herd animal object, of course, because herd animal is abstract. But leader here could certainly be referring to a horse. Now, cow's isGoodLeader should return true if the other herd animal is also a cow and is at the same approximate location. So we need a way to test to see if leader is actually pointing to a cow and not, say, a horse. And we can do this with the Java operator instance of. So the test leader instance of cow returns true if leader is actually pointing to a cow. To be exact, it returns true if leader is pointing to any object that is a cow, but we don't presently have any subclasses of cow. You can use this test on any reference to check the true type of its target. You give the reference, or any expression that results in a reference, the keyword instance of, and the name of a class. So that's the other end of the template method pattern in herd animal. If we call step on a cow object, we'll actually get the herd animal step, but the herd animal step will call cow's override of isGoodLeader, since isGoodLeader is abstract in herd animal. Now, just to be complete, read the horse class and answer this question. Describe what's necessary for a herd animal to be a good leader for a horse. And returning from a pause, well, looking at the horse code here, horses only follow other horses that are nearby, and then the leader's length of velocity has to be greater than our length of velocity, which boils down to we only follow horses that are moving faster than us. So if we call step on a horse, we'll get this rule for leader selection instead. Now, we've now reviewed all the code for herd animal and its subclasses, at least the top half of herd animal, that is. Let's take a look more closely at two object-oriented design patterns that appear in that code. Now, the first of them is the iterator design pattern. I said in a previous segment that iterators were common in object-oriented design. They're so common, in fact, that the very idea of an iterator a separate object representing an iteration, is one of the standard gang of 4 design patterns. So let's look a little more at this pattern and why it's so useful. Now, we could have written the loop in step here without an iterator. I mean, why all the fanciness? ArrayList, for instance, has a size method that returns the current number of objects in the array, and a get method that returns an object in the array by its index. So why didn't we just use code like this to iterate through the all list instead of all that iterator fanciness? Good old familiar I equals 0, I is less than size, I plus plus sort of loop. In a word, the reason is flexibility. This loop will only work with an array list. But what about classes that hold collections of objects but are not indexable, for instance, don't have a get method? The Java libraries include ones like that, as do many third-party libraries. Code that presumes we can walk an index through the collection won't work for those. But virtually any class holding a collection can provide an iterator. The iterator class represents the essence of iteration. To iterate, you need to advance to the next position, and you need to get the next item, and then you need to know if you are done. And that's it. If your loop assumes only those essentials, it can work with any type of collection. Now, let's see, just to make it a little clearer, how an iterator might be implemented. But first, a small confession, by the way. When I said earlier that iterator was a class, I lied. It's actually an interface, a base class that has abstract methods next and has next, but no actual code for doing the iteration, as I'm showing it here in the diagram now. What ArrayList's iterator method returns is a subclass of the iterator interface, one with implementations of has next and next that work on array lists. Now, here over in the other side is a possible implementation. We'll do more on interface syntax later, by the way, but you do need to know for this example that Java uses implements when deriving from an interface rather than extends. Aside from that, this is fairly straightforward code. And I'll ask you now to read it through carefully with an eye to the step iteration that we were looking at earlier, this guy here. Kind of walk through what that would do, assuming that iterator, ITR, is one of these guys. And read it through carefully, because just to keep you awake, there's a bug in this code here, and I'll ask you to find that, of course. So a reasonable pause, I would expect, and after reasoning carefully through the logic of the code, the answer, where is the bug, is it's right down here. That less than should be or less than or equal to should be a less than. Once we've reached my list.size, we have no more values to return, array lists being indexed from 0, so that should be a less than. Now, if you thought you needed an index equals 0 in the constructor, because the constructor isn't initializing index, now remember that it's a reasonable guess, but member data get 0 initialized for free, and I'm just sort of counting on that here. Okay, now here's question 5. Surely the ArrayList iterator subclass, the actual one, isn't called whatever. So what is the class name of the real ArrayList iterator? And we can't use it without knowing its name, can we? We have to have that. After a pause, this is a bit of a trick question, I have to confess. We don't know the name of the actual ArrayList iterator class, and we don't care. We'll just use an iterator reference, as we do in the animal code over here, right there, to refer to it. And we'll call its methods polymorphically. We never need to know its actual class name. Indeed, only ArrayList's iterator method needs to know the real name in order to create the object to return to us. So what we get back from ArrayList iterator is one of these guys, although it's not a whatever, it's some other name. It implements iterator, and we don't need to know anything more than that it implements iterator, because we can then use its methods polymorphically with an iterator reference. And so we've arrived at a point where polymorphism lets us refer to and use an iterator subclass whose name we don't even know, and whose code we'll probably never see. It's not bad for an obscure little language feature. But there's more. A different type of collection, say linked list, would return a different subclass of iterator, one with implementations suitable for that class. Instead of an index, it might contain or maintain, for instance, a pointer to one of the list nodes. So this here in a iterator for a linked list would be next node instead. And just to be sure the point is clear, what if any change is necessary in the for loop in step here if we change all from an array list to a linked list, with a completely different internal implementation, of course. And assume linked list has an iterator method, by the way. Turning from a pause, the answer is no change at all. Polymorphism will still call the right methods, using the linked list iterator to walk through the linked list. So the iterator pattern and the iterator interface let us write iterating code that is completely independent of the underlying collection. We could write a new collection class 10 years from now, plug it into herd animal, and that step for loop would work with it, as long as our new collection has an iterator method that returns an iterator subclass. Okay, finally then, just to illustrate that the iterator design pattern extends past even collection classes, here is a really strange iterator, which we'll label accordingly. And a question, really look at it yourself. It's not that much code, even if it is a little strange. What does it do? What's going to happen if I call next and has next on this thing? Returning from a pause, it returns a series of strings of the form number and then some value, whatever's in counter. It'll actually start with number 0, since counter gets auto-initialized to 0, right? And then it'll reach the end of the iteration after number 99, since hasNext, of course, returns true only if counter is less than 100. So this iterator has nothing to do with the collection. It just returns a series of strings. Iterator really does represent the essence of getting a sequence of objects. It doesn't necessarily even have to walk through a collection. It's not uncommon to find iterator patterns used in this way. There are even some languages, for instance Ruby, where a sequence-generating iterator is the standard way to do a for loop. Now, this is a good time to look at the GOF chapter, the Gang of 4 chapter, of the iterator design pattern, at least the first page of it. So please look that up. It's a good high-level summary of the iterator concept. The later pages in that chapter, by the way, we'll come back to in the next topic, so don't worry so much about them. But please do answer this question from that first page. The UML diagram on that first page shows a simple arrow from list iterator to list, which are classes comparable to our ArrayList iterator and ArrayList. What does that arrow represent in UML notation? Look it up in your chart, of course. And just the term is all we need for now. We'll discuss the meaning in a bit. And returning from a pause, and hopefully some reading of Gang of 4 and a bit of UML lookup, the line by itself, this line right here, represents an association between list iterator and list. And the arrow, specifically on the end of the line, represents navigability from list iterator to list. Now, what does that mean? Well, UML diagrams show a simple line connecting two classes when the classes have a relationship. That's the association. And the relationship has to be important to the design. Obviously, list iterator iterates through a list, and a list is iterated by a list iterator. That's an association. But associations aren't always symmetrical. More often than not, they're implemented by one class having a pointer or reference to the other. The whatever iterator up here in ArrayList, for instance, has a reference to an ArrayList as a member datum. It would be hard to imagine an iterator on a list not having such a reference. It needs to get to the list to retrieve each successive object. The reverse, however, is not true. A list class doesn't need a reference to the iterator object that works on it. And UML then represents this situation by an arrowhead on the association line showing in essence who refers to whom. List iterator has a reference to list, not vice versa. The arrow is optional. You can omit it if the association is a more abstract idea and there's no actual reference involved, or you can have arrows going both ways if both of the associated classes have references to one another, as is sometimes the case. Now, a final note, Gang of 4 actually uses OMT, an older diagramming system. And in OMT, that arrow signifies something called a uses relationship. But UML is based on OMT, and the OMT uses relationship is almost the same concept as the UML navigable association. When you read Gang of 4, you can substitute the latter for the former. Now, our last little bit here is on another design pattern that's quite a bit simpler to explain. The roster design pattern. In herd animal, we, as you know, maintained a static collection of all the objects of the class herd animal in this member datum all. And each object added itself to all in the constructor to maintain that list. This is actually a common thing to see in object-oriented designs, and it deserves its own design pattern name. It's not one of the Gang of 4 lists, so we're going to give it our own name, which is roster. Tracking all objects in a class via a static collection with a constructor that adds each object to the collection is a roster design pattern.